Good afternoon, Kimberly. All right.
Good afternoon.
And good afternoon, Justin. Thank you. Good afternoon, Alyssa. All right. Good afternoon, Jenna. Good. Hello, when you, and I know you were totally early. Thank you. Yeah, well, I know many of you were, but okay. Anyway, you and I was totally late. But anyway, good afternoon, Eileen. Good afternoon, Erin. Good afternoon, Rachel. Good afternoon, Erica. Good afternoon, Andre. Good afternoon, Sheeran. Good afternoon, Heaven. Good. Okay. Um, all right. Oh, thank you. That one I had to think about. Oh, so Gaz or a guy, like good afternoon, Yabo. That's good. I was worried that was a reminder of something that I've forgotten, which I'm sure I have. But okay, cool. Hello, we are getting there. I'm getting sad. I'm getting freaked. You're probably less sad than freaked. Don't be freaked. One thing that I'm freaked about is what I have not yet done, but I am going to do shortly, soon, is post to you. I have not yet. I'm looking to do that. I'm going to give you guys the rough draft of the final exam, so to speak. You know, you can call it a practice exam, you can call it whatever. I'm going to, it might even happen by the end of this class, although maybe not. It should happen shortly, like by the end of today or so. But when you get a document in your box called pre-final exam or rough draft of final exam or whatever, that's exactly what it is. You obviously don't have to turn it back to me. It's just the sneak preview of what your final exam will be when it's officially posted next Monday night or thereabouts. I do want to get it to you in time for you to be able to look at before next Monday and ask me questions about it on Monday. That's the idea. I mean, there's nothing else to do left in this class. You can still retro stuff if you want, but basically at this point where we are, hold on, sorry, this is all crazy. Like, I view it as my job to get you this final exam as soon as I can. Whatever I get you will then, be subject to revisions or corrections or updates that I'll try to tell you about by Monday. Your job is to, once you get it, to look at it and ask me questions Monday. I may still want to say stuff about physics Monday, but the idea is by the time we meet for our last class on Monday, certainly it should be clear what the final exam is, and you should have taken advantage of that fact to ask me questions Monday. When I say I'm going to post it, by the way, I'm also hoping to post it simultaneous with solutions. I'm hoping. So that will hopefully also make things clear. Let me just say again, though, what is going to be on the final exam is definitely a Doppler effect problem, and we're going to continue to talk about that today, a circuit problem. And I've said nothing about circuits in this class, but I know you've dealt with them with Woo, or at least that's my understanding. So it won't be a crazy circuit problem or whatever. And again, there will be a sample of it in the rough draft final exam that I post to you. So there should be a circuit problem, a Doppler effect problem, and then one general unthingy thing problem that will tie together what you know about the wave equation with whatever last things I want to say about fields and how this all ties together. But you'll see that. So again, whatever I post to you when I get you this document, it is basically the real thing. It's not representation. It is the real thing, except to the extent that I find errors or things that need to be updated or fixed for your class. But you can assume once you get this document that it is basically it. And any extent to which it's not it, we'll discuss on Monday. Okay. So the first thing I want to add, so one big part of it is this whole Doppler effect thing. Again, we've spent so much time, I think we should know it. I want to spend some minutes today, again, maybe slightly more slowly, telling you why I think the Doppler effect is so significant. Wait, people are coming, sorry. But first, to slow down slightly, it's definitely on the final exam. And when I say it, again, I mean, you should be able to solve any of the 4 cases. And once you've practiced enough, you're going to see it's not as bad as a lot of other things I could ask about. It's not meant to be bad. It's just meant to be something I need you to know. So you need to be able to compute and solve for, well, let me back up. By the time you get there, or maybe even by now, when I say Doppler effect, you should know that means the, oh, no problem. No, thank you. No problem. No problem. All good. Private chat person, but thank you. Like if I say Doppler effect, here's what you should picture. And maybe, I don't know if you want to write this down or if you already have a million times, you should picture that some source of a wave, you should picture that some source is sending a wave to some receiver, and that either the source or the receiver has motion, has velocity relative to the medium for that wave. So you should picture a source, you should picture a medium, you should picture a receiver, you should picture that there's some kind of motion of one relative to the medium. And you should picture that what that means then is that whatever the frequency of the wave as measured by the source will not be the same as the frequency as measured by the receiver. Like, it's always a little bit complicated to say, but that is the issue of the Doppler effect, that receiver and source will not agree on frequency. And when I say they won't agree, I mean they'll get two different measurements and they're both right in their respective reference frames, right? And therefore, to solve a Doppler effect problem means that if you're given the frequency as measured by the source, you should be able to find the frequency as measured by the receiver, no matter what case you're actually dealing with. So you should also picture, more people are coming in, sorry. So again, just to repeat, but just to try to make this as clear as possible, I believe there's four basic cases or four basic permutations of this. It could be the source moving in or the source moving out, or it could be the receiver moving in or the receiver moving out. And for in and out, you often use the words approach and recede, right? You shouldn't have a basic procedure from me that allows you to solve for the unknown received frequency under all of those cases. You should do the same procedure under all of those cases. Your procedure should be the one that we're doing in class. It should not be the random equation that you will find on the web and that will cause me great distress if I see it on the exam. So you should be able to solve for the received frequency by first solving for a wavelength according to source, and then using that wavelength according to source to solve for the frequency according to receiver. Like, that's the basics, right? But then as of yesterday or as of 2 days ago, the thing that one of the things I'm drumming in is that if you can do that, if you can compute for any case, no matter what, and if you can compute by the same procedure for any case, you should really see in your procedure that you end up getting different numbers for all the different cases. You should be able to see why that is slightly surprising. Like, that's a weird thing for me to ask. It's also why I'm like going over it again and again and again. I'm saying that if you really, really get the Doppler effect, you'll get why, on the one hand, we might, as physicists, expect that a receiver approach case and a source approach case we would expect maybe that they might yield the same result. And yet they don't quantitatively. Now let me be more, right? That's important again, like, and that's confusing, because I'm saying if you really get this, you should get why something would be wrong, but then get why it's actually right. I can't even, wait, let me say that better. Well, no, okay, here's a better way to say it. And here's why I'm saying it over and over again. What you really should get, and hopefully I will have a sheet on this in the final exam posting that will make this clear, why I'm saying this over and over, why I'm saying source approach versus, oops, someone else is coming, sorry. Hold on. Okay, let me say that slower. And again, I want to write this down, but I feel like I have written this down a number of times. It's in the packet of notes, and I'm also scared that if I start writing this down, I'm going to get myself off on a tangent or something. So let me back up and say this. And this is part of the final exam. You'll see it in the document when I give you the document. But like, it's one thing to solve the 4 cases of the Doppler effect, and you should be able to do that. But then the next level of really understanding the Doppler effect and its implications is, imagine what would happen, what kind of seeming Doppler effect would occur if, instead of throwing out wave pulses, if a source were repeatedly throwing out particles like BBs from a gun or baseballs from an arm, right? This is what I was trying to say Monday, and I want to say slower now, like, and this is part of the final exam, is you should be able to qualitatively and quantitatively imagine, like once you've practiced the Doppler effect enough and you get how it's deploying the character of velocity and the character of waves all together, then to really appreciate what the implications on waves are, you should be able to back up and imagine and actually solve the problem instead for a stream of particles, which is what I was starting to say on Monday. Like, instead of me in other words, you can't just blindly memorize the equations. Imagine if instead of me throwing pulses of sound, instead of throwing compression packets of air molecules at you at 340 meters per second relative to air, imagine that I'm shooting one BB after another at you out of a BB gun, or throwing one baseball after another at you. Okay, we can do all the same calculations. And we will find if I'm throwing particles at you one after another, that on the one hand, and let me say this as slowly as I can, and again, I part of me thinks I should be writing this down right now, but I definitely think you should be, if you can follow what I'm about to say. If I threw a bunch of BBs at you one after another, so it's like a machine gun of BBs, right? Then on the one hand, something very similar to the Doppler effect would occur. And that is this. What would happen is, if you were running toward me while I shot those BBs at you, you would definitely be hit by BBs more frequently than I was firing them. And I do want everybody to understand that. I want you to picture that. Like, in some sense, that's the easiest, most logical way to even understand why the Doppler effect is happening in the first place. Like, if I'm just sitting here shooting like one bullet every second, one BB every second, right? If I'm shooting one BB every second, but you're running toward the BBs while I shoot, I hope you can see in your mind that you would receive BBs more often than one BB every second. Like, I'd be firing them at one BB every second. That would be the frequency of firing as measured by me, and it would be correct. But if you're running toward them, they're going to hit you more often than one every second, because because they're all traveling through space at the same rate as they ever were, and they're all just as far apart from each other as they ever were. But now you get hit by one, and now you're running toward the next one as it's coming in toward you. So less time is going to elapse by the time you hit the next one, right? So if you were running toward the BBs, you would receive them more frequently than they were shot. That sounds very much like a Doppler effect. And on a very general conceptual level, that is very much like a Doppler effect. It almost helps to help you picture the Doppler effect. But here's the catch, and here's what you should be able to solve if and when I ask you. The thing is that if I were running toward you rather than you running toward me, if I were running toward you while firing those BBs, like if I'm firing one every second, but I'm running toward you while I fire, while you're standing still, then there too, you would receive them more frequently than if I were just standing still. Again, that sounds like a Doppler effect, and conceptually it is. Like, if I'm running to meet you while I fire, that's going to have a dramatic effect on the frequency received, just like if you were running toward me, that would have a dramatic effect on the frequency received, right? So far, everything I'm saying sounds just like the Doppler effect. And so far, everything I'm saying is just like the Doppler effect conceptually. So let me even say it more slowly. Whether it's waves or particles, if the source moves in or the receiver moves in, either way, the received frequency will, whoops, someone's coming, sorry. If the source moves in or the receiver moves in while this transmission is occurring, either way, with waves or particles, the received frequency will be higher than the source frequency. Like, either way, whether the receiver comes in or the source moves in, and whether we're talking about waves or particles, right? By the way, similarly, either way, whether the source moves out or the receiver moves out, then the received frequency will be lower than the source frequency. Either way, and either way, or whether we're talking about waves or particles. But the big catch here that is really important, that is really subtle, that you really want to try to write down or ask me in the chat if you miss this, because it's like the point, is that the difference between waves and particles is that even though conceptually, qualitatively, in both cases, an approach will yield a higher received frequency than the source frequency, in the case of particles, it doesn't matter whether the source approaches or the receiver approaches. The increased frequency, the Doppler shift, so to speak, will be literally identical whether the receiver moves in or the source moves in. It won't make any difference because there's no medium. Like Earth moving towards sun is identical in all respects to sun moving toward Earth. Okay, so if I were shooting BBs at you while I'm running, then you'll receive more BBs than I shot. You'll receive BBs more frequently than I shot them. And if you're running, you'll receive more BBs. Sorry, I'll say that again. If we're talking BBs, and please try to write this down some way. If we're talking about particles, whether the receiver comes in or the source comes in, both cases, the received frequency will be higher than the source frequency and by exactly the same amount. Like the Doppler shift, the new frequency, the solve for frequency, the answer to the problem would be indistinguishable whether the receiver came in or the source came in. But if it's waves that I'm shooting, then whether the receiver comes in or the source comes in, yes, they'll both found frequencies, both received frequencies will be higher than the source frequency, but they won't be the same as each other. The Doppler shift will be different if the receiver comes in versus if the source comes in. That is only true of waves, and that is the true character of the Doppler effect. Let me say it one more time. If the source moves in versus the receiver moving in for waves, yes, both cases will get a received frequency that's higher than the source frequency, but the exact amount will differ for the two cases. In other words, for waves, there's 4 different cases and they yield 4 different answers. But if we were doing it with particles, there's 4 different cases, but it's 2 pairs of identical answers in the case of particles. And you should be able to solve for either one and compare. And I'm going to even try to say that one more time. But the reason this is so important and so subtle is, it seems all this stuff is sort of obvious when we're talking about like sound versus baseballs. Like we know sound, or I think we know at this point, sound is a wave and baseballs are particles. So, and they're macroscopic and they're somewhat easy to picture. And the wavelength of sound, we keep saying like a middle A on a piano has a wavelength of like 0.77 meters. That's like 3/4 of a meter. Like that's macroscopic. Like the distance between air pressure pockets in a sound wave is really visible and measurable, right? And you can even like get in an airplane and speed up toward the speed of sound and collect a whole wall of sound next to you and then get faster than that and crash through it and make a sonic boom. Like it's pretty evident that sound is a wave, and it's pretty evident that baseballs are not a wave. But now imagine, and I know you've heard this in other classes a million times in a million different ways, imagine that we now get down to the microscopic level, and whether it's like the turn of the 20th century or the turn of the 21st or 22nd century, if we're dealing with particles like electrons or quarks or photons, whatever these things are, if we're dealing with tiny, tiny particles, it starts becoming less and less obvious whether they exist as little things or whether they exist as pulses in media, right? Like the wave, you've heard the wave particle question, I believe, or you've heard allusions to it in other classes many times. And I want to end this course really, really drumming in how deep this question really is. And so first thing I want to say is once things are small enough, it's not obvious whether they are things or not. Or let me put it a different way. The question of whether anything is a wave or a particle, the question of like, for example, light, whether it is a wave or a particle, which is sort of like ultimately what I want to have addressed by the end of today and the end of Monday. Like, I know you've heard it a million times, and I know it's like a cliche that's almost boring at this point. And let me even say that when I was a physics major in college, like I heard it so many times, I thought it was a stupid, cliche, annoying question by a certain point in my education. Like I kept hearing, is light a wave or a particle? Or even better, I kept hearing what I think you guys hear, which is for centuries and centuries, people debated whether light was a wave or a particle. For centuries and centuries, people thought it was a particle. Then people thought it was a wave. And then finally in the 20th century, we found out, oh my God, it's both. Isn't that crazy? Quantum mechanics, whoa. I heard something like that. And I think probably you've heard something like that. Now, I love physics now, and I loved physics when I did, but I hated hearing that. It got me so annoyed and so bored hearing that over and over. Is light a wave or a particle? It turns out, can you believe it? It's both. Whoa. I was like, there's no whoa there at all. That's the stupidest thing. I thought that was so dumb and annoying that I kept hearing it, partly because they kept saying it like that. They kept saying, we didn't know if we thought light was a particle, then we thought it was a wave, then we thought it was a particle, and then, although it never occurred to us ever, all of a sudden, all these physicists from all over the world got together and decided it was a wavicle, it was both, and our minds were blown, the end. And I was like, first of all, the reason I thought that was stupid, and maybe you do too, and fair enough if you do, but first of all, I just got bored of it because I just heard it so much, like, and I didn't know what I was supposed to do with it. But second of all, I thought it was stupid after a while, because to me, that sounded like saying, we thought the ice cream was chocolate. Then we thought it was vanilla. Then we thought it was chocolate. Then we thought it was vanilla. And then, even though no one had ever thought of this before, suddenly we were like, it's a swirl. It's a chocolate vanilla swirl. Isn't your mind blown? Right? Oh, sorry. Okay, fair enough. I love Cartman, actually. All right, thank you. I'll take that as a compliment, sort of. But I hope I never treat my mother the way he treats his mother. But wait, what was it? What's the funniest? Sorry, you told me this. But my favorite Cartman thing that I cannot say in public, but when he takes out the oh my God. Well, anyway, all right. Yes, I love Cartman. Okay, that is hilarious. But okay. No, thank you. But I love when he's like, excuse me, and he takes out the megaphone and says the most anyway. But yeah, no, I thought that was so dumb because in my mind, every time they said, is it a particle or is it a wave? It was like saying, is it chocolate or vanilla? And what I was thinking was, first of all, whoever said that it couldn't be a swirl? Like, are you idiotic? Like, are you telling me for centuries, people are like, is it this thing or that thing? And no one ever entertained the possibility that something could be both? Like, why can't something be vanilla and chocolate? Furthermore, I was like, what happened to strawberry? Like, who said those are the only, like, why does it have to be a particle or a wave? Like, couldn't it be some other thing that you haven't investigated yet? Like, why are physicists so arrogant as to think that everything has to fall into the two categories that they just happen to have discovered so far? Like, how dumb is that? That's what I thought. And I'm not saying I was dumb for thinking that. I think I was right for thinking that because I think it was badly presented to me. Here's what I want to tell you guys, like part of the purpose of this class. And again, even knowing that we didn't get to everything that we could normally get to in a non-COVID year, I still want to get to a major punchline with you. And here's part of the punchline. This class is about thingy things versus unthingy things, right? Or better yet, this class, well, really, Physics 203 is about the motion of thingy things. This class is about the motion of unthingy things. Or better, I should say, Physics 203 is about thingy motion, and this class is about unthingy motion, right? What I mean by that is like, now that we've like spent all this time studying sound, and in the lab, you're looking at like electron flow, and I'll try to say something quick about that before this class is over too. But what you've been looking at for a while, after we did all this hard math to like first look at one thing wiggling back and forth, and then put a bunch of wiggling things next to each other and say, oh my God, if they all wiggle in a certain way, then we get this pulse that goes through. Right. And by the way, that's just exactly what's happening in all the electron. I will say it now. Like you might think, what does any of this have to do with what we're doing in lab? Like what? This all seems completely disjointed. And I apologize if it probably does seem that way. But here's one big connection between what we've been talking about with sound and what you're doing with Woo in the simulation labs is that no electron goes around the entire wire from the negative terminal of the battery to the positive terminal of the battery. Like I know we're always talking about, we're trying to picture like electrons moving around and we call that current. And you're all smart enough to know like, wait, but electrons are negative, so they're going that way. So I guess, am I supposed to be picturing protons going that way? Like, that's confusing enough. Like, am I supposed to be picturing an electron going backwards from the negative to the positive? Or am I supposed to be picturing a proton going from the positive to the negative? And then you might even know enough from chemistry to have heard of Brownian motion or to have heard of drift velocity or things like that. And you might even be knowledgeable enough to know, like, wait, how are the electrons even doing that? Like, are you really telling me that like an electron is actually, like a free electron is actually traveling all around this wire from the negative terminal to the positive terminal? Like, and you might say, I mean, one thing that you definitely, hopefully are seeing in lab, this sounds like a digression, but here we are toward the end. So I'm really trying to wrap up things for you guys. One big principle in the lab with all these electrical circuits is that current is always a constant value throughout a loop, right? I mean, obviously, if a wire branches into if the trunk of a wire branches into two parallel choices, then some current goes one way and some goes the other way. But for any given loop, we treat the speed of the current all the way around that loop as one number. We call it current. We say it's like 300 milliamperes or something. And you might well have wondered, like, really? Really? Like, all the electrons are really traveling the same speed? That seems like quite an approximation. Or you might even have thought, hold on, V equals IR, like, okay, the current is flowing because of potential difference. And yeah, we're supposed to make some kind of analogy. It's kind of like, and I think Wu makes a lot of analogies to like traffic through tolls and bridges and stuff like that, I think, or at least he does to me on the phone. And you might really understand or be understanding that the potential difference between two places in the current is like gravitational potential difference between two locations on Earth, and that due to potential energy, things get kinetic energy and then they move, right? Like, hopefully you do sort of understand that in the currents, but it might have crossed your mind at one point to be like, but wait a second. When things fall to the ground due to gravitational potential energy, they get faster and faster while they're falling, and their kinetic energy increases. But in these electrons that we're talking about, like, if we believe everything Wu is saying, like, they're falling from one terminal of the battery to the other because of electropotential difference, i.e. voltage. Like, they're falling because of voltage, and voltage is supposed to be like gravitational potential energy difference. But when things fall due to gravity, they get faster and faster. And when these charges move around the wire, Wu keeps telling us that the current is the same everywhere in the wire. Like, nothing's getting faster. They're just like moving at constant speed. So that might have confused you at one point, or it might raise questions or objections in your mind. Like, what is going on with this analogy? How is it that all these electrons are moving at the same speed? Here's the answer. They're not. Not that Wu's wrong, and not that anything you're doing in the lab is wrong, but here's the deal. No electron is actually ever making a trip from the negative terminal of the battery all the way to the positive terminal. I'm not contradicting Wu, and maybe, by the way, maybe Wu has said this as well. God bless, Quark bless him. But what's going on? There's no electron moving from the negative terminal to the positive terminal any more than is there any air pocket or air molecule moving from my mouth to your ear when I scream and send sound to your ear. When I send sound to your ear, I'm sending an unthingy motion, right? I'm sending a pulse through a medium of air molecules to your ear. The only things moving are air molecules, but no air molecule is making a journey from my mouth to your ear. That's the essence of wave motion, right? That's the essence of what we call unthingy motion. Well, same thing in the circuit. It's half the reason you're spending all this time on circuits. No freaking electron is doing anything like that at all. Each electron is just zigzagging around in a sort of Brownian way in its little neighborhood. But then it goes, one electron near the negative terminal of the battery, like, goes back and forth, and then the electron next to it goes back and forth, and then the electron next to it goes back and forth. What we're doing is sending a ripple through. Whoa, what just happened? Oh, sorry. We're sending a. Sorry, hold on one second. Someone, this chat. Wait. Oh, okay, cool. What we're sending, what current is a pulse. In fact, a compression pulse, much like sound. It's a vibration, an oscillation that is pulsing through the whole medium of net electrical charge. Electrons are moving, but only in their neighborhood. On the whole, what's traveling through the wire is a charge pulse. And pulses always travel at a constant speed relative to their medium. That's why we can say that current is essentially a constant throughout the wire, because what's constant is the speed of that pulse. It's an unthingy motion that then is so reliable and so controllable and so measurable, even though we can barely get down to see those electrons. We can barely control any individual. We can't control any individual electron any more than we can control or predict any individual air pocket or air molecule pocket. What we can measure and predict and observe and control is the pulse of sound that propagates through the medium of air molecules. And what you're doing in the lab is controlling, predicting, measuring, analyzing the pulse, the compression pulse that is propagating through the medium of net electrical charge. First of all, that's the connection between what you're doing in lab and what you're doing here. Sorry if I didn't mention it before. Second of all, that's why the stuff in lab actually works and makes sense, because what's really happening is waves underneath it all. Okay, now I'm not saying, well, yes, I am saying, right? And that's why we can say that current is constant. For the same reason we can say that speed of sound is constant. It's constant relative to its medium. That's the fabulous property of pulses that is so delightful, like in a practical sense. Like electricity is like the most practical application of all of this, right? But then philosophically or theoretically underneath it all, it's fabulous that what we're looking at, whether it's in the lab or here in the Doppler effect example, we're looking at motions of things that aren't things, right? Like, to bring this back full circle now, again, just to try to tie up loose ends, or so that you understand what the point of this course was, or what's going to be asked of you in the final exam. What we're about here is unthingy motion, motion that is real, that's predictable, analyzable, observable, measurable, controllable, right? But is not associated with any one discrete or identifiable or countable particle. Again, sound is real. And the only thing moving, sound in general cases, sound is real, and it arises because of the motion of air molecules. But when sound goes from me to you, no individual air molecule goes from me to you. That's what I mean by unthingy motion. And same thing with electricity. Like, electricity only happens because of the motion of charges, ultimately, let's say free electrons. But when electrical flow occurs from here to there, when a current passes from here to there, no individual charge, no individual electron actually makes a trip from here to there. Like, that's an enormous journey for an electron, first of all. I mean, and it might accidentally, but just like an air molecule might accidentally go from my mouth to your ear, but that's not what it is that we're tracking or measuring or controlling when we talk about sound, nor is it what we're talking about when we talk about electrical flow. So this course is about the motion of what we would call unthingy motion, what I'm calling unthingy motion, what people in the real world would call either energy flow, or I really think the best word for it is information flow. Like, that's what we're really talking about in this course, is how information moves according to the laws of physics from one spot in space to another, whether it's sound or electrical current or whatever. What's really moving is a number, right? Like a frequency. Right? Like we said a couple of weeks ago, if I sing a perfect middle A, which I cannot, but if I sing a middle A and you hear a middle A, what got to your brain was a number, the number 440. And that number somehow got preserved, even as it went from my tongue through air molecules, through cartilage, through electrical impulses. Like, some kind of pulse went through a bunch of different media, changed its speed a bunch of times, changed its wavelength a bunch of times, but preserved somehow its frequency of vibration. And that number, that frequency, is what ultimately got to you. That's why I say it's the flow of information. It's a freaking number, not a numeral, not like Sesame Street, not like not like a plastic like number, which would be a numeral, but like a number, a quantity. Okay, now, having said all that, and again, I apologize if that's like all obvious, or if you're getting sick of hearing that, but I sort of, so when people have asked throughout the centuries, or people repeat to you the question from the centuries, when people say, is light a particle or a wave? Well, Yeah, that makes it sound like we're saying is light this kind of thing, or is it that kind of thing? And like, who knows? Maybe there are other kinds of things in the world. Like, why is that such an interesting question? It's a misnomer. It's a bad way to ask the question. When they say, is light a wave or a particle? It really, at least to me, makes it sound like we're just trying to categorize light as like a vanilla kind of thing or a chocolate kind of thing. And it kind of makes it sound like we haven't even acknowledged the possibility that there might be strawberry things or swirly things. It sounds like a stupid or kind of arbitrary or arrogant question. But now that you've had this whole class almost, and now you've had all this lab experience, rephrase the question in your mind. When people ask, is light a wave or a particle? What they're really asking is light a thing or not? What they're really asking is there such, like, we see the phenomenon of light, like, or we see things by virtue of light, we see colors, blah, blah, blah. We observe that light exists, much like we observe that sound exists. But with sound, when we say that sound is a wave, what we're really saying is there's no such thing as a sound thing. There is no thing that makes sound or even is sound, right? What we're saying is, like, there's air. And if air moves in a very, very specific way, if not even one air molecule, like one air molecule is not enough to make sound. So first of all, there's no such thing as a sound particle. Second of all, even if you want to say, well, sound arises because of the harmonic oscillation of like air molecules, even there, no, that's not good enough, because one air molecule oscillating harmonically is just that, a harmonic oscillator. Like the first freaking month of this, or 2 months of this course, which probably drove you all crazy. But one air molecule going back and forth is just that, one air molecule going back and forth. That ain't no sound. In order to have sound, you have to have a whole bunch of air molecules, each of which is going up and down in a very specific way, and then each of which is going up and down in a specific way, like in relation to the one next to it, right? A sound wave is an oscillation of oscillations. It requires, as we keep saying in this class, a collection of particularly precisely staggered oscillators, right? So that's to say, it's not a matter of technology and it's not a matter of discovery. No matter how good your microscope is or your iriscope, like no matter how closely you look, you're never going to find a sound thing. There's no such thing as sound. Sound is not a noun, it's a verb. Like it's a phenomenon, an activity undergone by many, many particles. So much so that not only do you need a bunch of air molecules to make sound, but in fact, as you all know, you could send sound through water or wood. Like it's not actually any property of the air that actually makes for the sound. It's just that air is like the common way to do it. But sound is a propagation of a pulse through a medium. And the medium itself is not sound, and et cetera, et cetera. Sound is the whole phenomenon, right? So there's no such thing as a sound thing. There is only, so that's why I say it's like a verb, not a noun. It's something that a bunch of things do, and it requires extreme organization and precision to do it. So when people ask, is light, or when people have asked for centuries and centuries, sorry, this is a good question, I think. Yeah, wait. Yeah, I think, wait, I'm assuming this is not a joke. I think this is a very good question. It may sort of also be a joke, but I'm going to address this seriously, Yabo's question. Like, actually, so I'm going to take this seriously. Actually, I'm saying it's wrong to reduce certain things to a single word. Like the single word that I don't mind reducing certain things to the word particle. Like at least on a macroscopic level or whatever, some things are part. So let me put it this way, to try to answer that question. I'm not just saying that any categorization is stupid. No, categorization is fine. But what I'm really saying is that when people ask, is light a wave or a particle? That's a bad way to ask the question, because first of all, no thing is a wave in the first place. Like a wave is the better way to ask the question. In other words, so 2 points. First of all, what people really should be asking, and maybe they did in your classes, like I don't want to criticize your prior professors or anything like that. I'm just talking about my personal experience. But first of all, the better way to ask a question really is is the motion of light particle motion or wave motion? Like, first of all, I think that's a better way to ask the question, because there are two types of motion in this world. And that's why we have physics 203 and physics 204 in a way. Physics 203 is about particle motion, meaning the kind of trajectories or the kinds of journeys that are undergone by identifiable, countable, discrete objects, which we call particles, right? So like when a baseball goes from me to you, at least macroscopically, if a baseball goes from me to you, literally we can say, there's the baseball right here now. Oh, there's the baseball right here now. There's the baseball right here now. Oh, the baseball got to you. Particle motion. But when sound goes from me to you, that is real. It's a real situation. It's a real motion. But there is no object at all that we could point to that's over here and then over there and then over there. There's just a pulse. There is this disturbance in the medium of air. Put another way, if I say that sound motion occurred from me to you, I can only even picture that if I first picture some kind of medium that's getting disturbed in a certain way. So so this is to Yabo's question and like to everybody. First thing I'm saying is, I think that part of the problem with the question is light a wave or a particle. I mean, I think it's a super important question. It's what I'm trying to end this class on. But I think it ends up sounding stupid if it's like not handled with care. I think, first of all, what people should be asking, or what people were asking historically, is the motion of light a particle motion or is it a wave motion? By which what they really meant, what they were really asking was, if we were to look as closely as possible as light, if we were, and they understood that whoever's ever asked this has always understood that technology was going to get better. All physicists always understand that physics is advancing, every step along the way. But when they ask, is light motion like wave motion or particle motion? First of all, what they're asking is, even if we imagine the most advanced technology possible, even if we extrapolate like all the way to the future or wherever, and we were able to look down really super closely at a light beam coming from a star into the earth or the sun, or if it's the 20th century, like light coming from a light bulb, toward our lab desk or whatever, what they're asking is, if we were to look really, really closely at light, would we end up finding anything? Like, is it made up of a stream of little things, each of which we could call a light thing? Or would we never, and that would be like the way we think, BBs from a gun are like you could shoot a lot of BBs from a gun. And if you stand far back enough while shooting a lot of BB, like a machine BB gun, I don't know why I keep saying BB, I just don't want to be violent. But if you picture like a machine BB gun shooting super, super fast, like BB, 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 and someone stood far enough away, like from far enough away, it looks like just a stream, like, or in a cartoon or something, it might even just look almost like a laser or something. But then if they got up close, they would see that there's like BB coming out and then a rest, and then a BB coming out and then a rest. Like, they would be able to separate BBs from not BBs. And they would see that stream of firing wasn't actually a stream. It was actually made of little things that we could call particles. Okay, BBs are like that. Sound is not like that. No matter how close you get, you're never going to find a little bit of sound. And that's not arrogance on my part. It's not like I'm saying technology never gets better. It's saying we already have good enough technology that we know when we look close enough, we see what's happening. Little air molecules are going, back and forth and back and forth. There's no sound particle. They're just air particles. And more to the point, no air particles actually going from the beginning of the journey to the end of the journey. Same thing with electrons in a wire. Right. So first of all, I'm saying when anybody's like interested in light, I'm looking at the time. Okay. When anybody through history or in your other science classes has ever talked about light, first of all, the question they're really asking is the motion of light particular or wave-like, right? Like, they're asking about, like, they can't really ask, is light a wave or particle? Because no thing is a wave. By definition, wave means not a thing. So what they're really asking is the motion of light particular or wave-like? And that's a fair question. And I think this is addressing Yabo's question. But then second, now I want to say to everybody why it's a deep question, why it's fair to ask, is the motion of light particle-like or wave-like? Because even when you say that, my reaction as a college student was, well, why are those the only two choices? Like, couldn't there be something else that we haven't discovered yet? And sure, there could be. And in fact, lots of waves are so much more complicated than the waves that we're talking about here. You could even argue that that's a whole third category, like complicated waves or something. But it doesn't matter, because what they're really, it sounds like they're asking, is the motion of light vanilla or chocolate? That's not what they're really asking. They're really asking, is the motion of light vanilla or not? Let me rephrase. What they're really asking is, does light exist as a thing or not? And when you put it that way, then I think it's fair to think there's only two options, right? I mean, that's true of anything. Like I could say, is this thing red or green? And you could say, dude, it's yellow. And like, end of discussion. I'm an idiot for having reduced. But if I say, is this thing red or not? That's a fair question, right? The answer better be one or two. I mean, even if it's yellow, then it's not red. If it's green, it's not red. Or if it's red, it is red. Like this is called the law of the, right. Okay. That's a good question. I'm going to answer. Yeah, that's a good question. Also, I'm going to try to directly address that. But well, yes. So I'm totally going to answer that in 1 minute. But that question also, Yabo's question does show that I feel like maybe I am making sense then for him to have just asked that, because that is what I'm getting at. Like I'm saying, when people ask, is something a particle or a wave? What they really mean to be saying is the motion that we observe particle motion or is it wave motion? And what they really mean by that is there a thing there or not? And what I want to say is that's a fair question. And what I want to say about that is and I will address his thing about photons, but what I want to say about that is when you put it that way, I mean, that's really what physicists or people, every kind of people have been asking since before Euclid's time. When people ask, is light a particle or a wave? What they're really asking is, does light exist? Is there a thing called light? Because honestly, at a certain point in history, we came to understand that there is not a thing called sound. Sound does not exist as a thing. It exists as a phenomenon. Like we could ask the question, is sound a thing or not? And the answer is no, it's not, right? And again, let me say, when we put it that way, when you ask, is something blah or not blah, let alone when you ask, does something exist or not? Then I think it's fair to think there's only two options. Right? I mean, literally, and you could pick any category you want. It doesn't matter how familiar with the category you are. I can ask, is Yaverbaum a space alien or not? And you don't say, well, I don't know enough about space aliens. There might be a third option. Like, no, all you have to know is about logic. Either I'm a space alien or not. Even if you don't know the answer, you know it has to be one or two of those answers. Or if I say, am I Bablipa or not? You might say, well, you need to define what Bablipa means for me to be able to answer, but you're not going to say there might be a third category. Like either I am or I'm not. That is literally called Aristotle's law of the excluded middle. It is the hub of all logic and at least all Western logic and Western math. The whole idea that you can't say something is and is not at the same time. That's a contradiction. Like maybe you can in a deep philosophical or Eastern way or whatever, but our whole math system and our whole science system assumes that something either is or it isn't, but it's not both and it's not neither. Now, to Yabo's question, the word photon is the word that is supposed to mean the thing of light, the particle of light. Anytime anybody does refer to a photon, they are referring to a particle of light. In other words, to address his question, to believe in photons is to believe that light is a thing. Okay, and I'm not telling you to believe that or not. I'll try to get into that more if I can. But yes, absolutely. This does get into issues. But how much do I want to say about this? Well, I'll quickly say this part is not on the final. Everything I'm saying so far, I hopefully will help you with the final. What I'm about to say right now is a little bit off kilter. But when Einstein got the Nobel Prize for the paper he published in 1905 called the Photoelectric Effect, the discovery of that paper was, in effect, the discovery of photons. Einstein was saying in 1905 that light did exist as little particles called photons. And that was a major crazy discovery because very recently, right before that, it had been fully established by the physics community that light traveled as a wave. And they believed that because of something called Young's two-slit experiment, which had been, they had believed that for 100 years. Young's two-slit experiment had been done in like 1804, I think. So this is where it does get, and now again, I don't want to confuse people. I'm not literally going to ask you this part on the final, but yeah, in the history of physics, it did go back and forth. Like Newton thought light traveled as little particles. He couldn't prove it. He just advanced a lot of argument. I mean, he couldn't empirically in the lab prove it, but he advanced a lot of arguments for the idea that light traveled as little actual things of light. His big rival Hooke, as in Hooke's law, as in half of what we do in this course, said, no, 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 that's not right. Light travels as a pulse the way sound does. Like, they knew enough about things to be making these arguments. Then, as of 1804, Thomas Young showed, beyond a shadow of a seeming doubt, showed in the lab, for reasons I cannot get into right now, but he showed, oh no, light, when light travels through two slits, it interferes with itself, like the crests of light cancel out with the troughs of light. And like, basically, I'll say this really quickly, Young sent light through two slits. And I know you've heard this in other classes, but again, it might not have sunk in what the point was. Young was able technologically to control light so nicely and so well, which it really was technically amazing. Like, we didn't have light bulbs then. So sunlight through, he used somewhat sunlight through a lens and also candlelight through a lens, but he focused the light so effectively and so thinly and so monochromatically that he was able to send light through two slits, much like we can send water waves through two gaps in a barrier. And on the other side of the lab, like on a screen where the light from these two slits hit the screen, there were places on the screen, more than one place, there were a bunch of alternating places of full darkness. Places, in other words, where light from one slit added with light from another slit and yielded darkness, which makes no sense if light is traveling like a baseball. Like, you never add one baseball to another baseball and get no baseball, but you can add the crest of a sound wave or a water wave to the trough of a sound wave or a water wave and get no motion, right? Like, waves have crests and troughs, and when crests and troughs interfere with each other, they can cancel out. And that's not a surprise with sound waves or water waves. Right, that's the double slit experiment, exactly. The original, Young's double slit experiment in Young. So I'm saying I'm all over the place and I'm watching the time. I'll try to get back, but these are great questions and they do. And this is, again, like, you might as well get something out, you all might as well get something out of this course if we're going to do all this. So yes, in 1804, and also if you're still with me in all of this, I'm remembering what I'm saying. So if I have to adjust questions on the final exam to make them about this rather than something else, I will. Like I'm not just trying to yell at you and waste your time, all of you. But like in 1804, Young sent light through two slits, and it's called the original double slit experiment. And there were places on the screen on the other side where light from one slit hit light from the other slit and yielded darkness. That literally makes zero sense if light is a thing. Like, I mean, it makes no sense. Like, how do you add a baseball to another baseball and have no baseball? But light plus light seemed to be yielding darkness. And it did so in a quantitatively very precise way that matched all these quantitative descriptions that then said to Young, oh my God, light must have crests and troughs. Like, and nobody could do this before because they didn't have the technology. They all understood the arguments. They were making arguments for centuries, but Young was the first person to really be able to control light so precisely as to do this. So he said to the world, oh my God, light plus light can equal darkness. That makes sense only if light is not actually a thing, but if it's a phenomenon, a bunch of pulses with crests and troughs that are canceling each other out and allowing light plus light to equal darkness, the same way that sound plus sound can equal silence, hence noise canceling headphones, right? Stuff like that. How do they work? They take the sound that's coming in, and for every crest, they send in a trough of the same frequency and it cancels out. Like, you can cancel out sound. You can't cancel out a baseball, so far as I know. So Young said, oh my God, here's the resolution for all time. Light is traveling as a wave. It is like sound. In fact, and please do remember what I'm saying now. I'm going to take one more little digression just to make the whole point, but like, I do want you all to know this, because that as of 1804, so please write, I'm afraid to write this down, but please write this down. As of 1804, Thomas Young's double slit experiment, and the exact date doesn't matter, but it's good to know that it's like in the early 19th century. So this is before Einstein, and this is before light bulbs, and this is before lasers, okay? Thomas Young showed us that light interferes in the manner of waves. So Young's experiment definitively showed, logically showed, that light was not a thing. It was not a thing. It was a phenomenon going through things. Again, please write that down. Like Thomas Young, 1804, double slit experiment. Light travels as a wave. According to that, light travels as a wave. Okay. To this day, by the way, I will say more. I'm still going to acknowledge something about what Yaverbaum was saying. But the reason I want you to write that down, and I'm asking you to write that down, because that somehow I will put that into the final exam, because here's the deal. As long as you see, like, the other things have happened since then, but we still take that idea super seriously. And we still do double slit experiments to this day. Granted, they have other implications as well. But one thing that we as physicists have held on to since 1804 is this idea that apparently light can travel in ways that demonstrate crests and troughs that can interfere, cancel each other out. And therefore, since 1804, we have said, oh, we have definitive empirical evidence that light travels as a wave, meaning that light is not a thing. And again, this means it's not a photon. Like, I'll get to that in a second. But as of 1804, we're saying, okay, Newton was wrong on this particular question. Hooke, our man Hooke from this class, Hooke's law, Hooke was right. We say as of 1804, thank you, Thomas Young. You are a brilliant technician. You didn't start any new logic that we never thought of, but you were able to show us in the lab what we've all wondered. And so we say, aha, light propagates as a pulse rather than traveling as a particle. Okay, that's what we say as of 1804. Therefore, and please write this down. If you're with me, this is, I promise, if you're still paying attention with me right now, you will be rewarded for this on your final exam. And those people who are not paying attention will falter. Therefore, and I think I mentioned this last time, but therefore, if you accept that argument, and it's a pretty good argument, like, oh my God, light cancels itself out and makes darkness. Well, crap. I mean, sound can do that, but baseballs can't. So if light propagates as a pulse rather than traveling as a particle, then the fact that starlight, which reaches us, always seems to demonstrate frequencies that are lower, i.e. more red, than the frequencies that they would measure from the star reference frame itself. I'll say that again. In other, starlight comes to, now I'm saying something modern now, but I'm saying in the modern world, in the 20th century, we came to realize from spectroscopic data. Now in the 20th century, we have spectroscopic and astronomical data that says that measures the light that comes from stars, and we're saying again and we're saying that if light travels as a wave, then the frequency of that light gets translated by our brain as color, just like the frequency of sound waves gets translated by our brains as pitch, right? So the astronomical and spectroscopic data of the 20th and 21st century show us that when starlight reaches Earth, the color that it demonstrates in the frame of reference of Earth is typically, very, very, very typically, lower than the frequency that it should or would have as measured in the star frame of reference. Now, and how do we know that? Because we know the chemical compositions of stars, and we know how spectroscopic data of chemicals works. Like, and that gets into your other science classes. But so we know what color or what precise frequency the light should be at, or would be, or was as it was leaving the star, or as it was measured by the star frame reference. And we see what frequency the light demonstrates when it comes into us. And invariably, not in every single case, but by overwhelmingly, the light that we receive on Earth is always a little bit redder, a little bit lower frequency than the light as it left the particular star. That the data overwhelmingly shows that. This is called, and again, please write this down. I'm sorry, I'm not writing things down, but I'm just afraid to lose momentum here. That is called the red shift of starlight. Like, you can Google it. And the redshift is just a cute, fancy name for the Doppler effect as demonstrated by starlight. If we believe that light is a wave, and if our data is saying that the light waves that we get from stars is redder than the light waves as they left the stars, what we have to infer, if we believe all of this logic, if we believe that light is a wave, which I'm just now giving you the one reason to believe, so I will put that on the final exam somehow. If we believe Young's two-slit experiment from 1804, that light plus light can equal darkness, then we believe light can travel as a wave. And if we believe light travels as a wave, then we believe the Doppler effect applies to it. And if we're observing a frequency shift between the starlight as measured by the star versus the starlight as measured by Earth, if that frequency shift is always lower, if the received frequency is invariably lower than the source frequency, then we have to infer that the source or the receiver, but in this case, the source is moving away from us, right? And again, and so first let me say that we infer that the source is moving away from us. And that is what we infer, that typically, overwhelmingly, by and large, no matter what direction we look in space, stars are moving away from us. And even weirder, it turns out no matter where we look from, it's not even just Earth, because like we don't believe anymore that Earth is the center of the universe. We believe that Earth can treat itself as the center, just like anything else can treat itself as the center of the universe. That's Galileo all over again, right? So it turns out wherever we're looking in the universe, starlight demonstrates a redshift, a Doppler shift toward lower frequencies. So we infer, oh my God, things are spreading out. The universe is expanding. That's where we get this idea of we believe the universe is expanding because we believe the Doppler effect. And we believe the Doppler effect applies to light because we believe Young's two-slit experiment. Now, I mean, hopefully that sort of makes sense. Like, I mean, this is one of the reasons I think this is such a big deal. On a side note, I have to say that is a really big deal. First of all, it's like about the whole universe, right? Second of all, you hear about it in the New York Times all the time, the expanding universe, the expanding universe. I just want you to know where that's coming from. Like, don't just accept that on, it's not just like scientists don't just want to believe the universe is expanding. They believe it for that reason. But third of all, in case it's never occurred to you, that is a really weird thing to believe. One of the reasons I get so excited about this, and I won't put this part on the final exam, but like when we say the universe is expanding, we're saying that the whole kit and caboodle is expanding. We're saying that the entirety of space and time is expanding, like the whole thing. And what the heck? I mean, how does that even make sense? Like usually when you say something's expanding, like if I say like the liquid in my coffee, like the coffee is getting hot, so it's expanding in my cup. What that means is that the coffee is taking up more of the container of the cup, meaning that whatever empty space there was in the cup before, now my coffee is expanding into that empty space. And so there's less empty space and more coffee. But if we say that the universe is expanding, we mean that all of it is taking up more, but taking up more what? It's not inside some other container. Like, what is it? Like, what is it expanding into? How could space, it's one thing for things to get farther apart in space, but if we say all of space is getting bigger, I literally don't even know what that means, but we're saying it because of the Doppler effect as applied to light. So now, and I know there's 9 minutes, and you can see why I'm taking my time getting you this document, because how I put all this into the document, Lord knows. But here's the thing, like first of all, Yaverbaum was right to allude to the fact that even after we finally resolved this question in 1804, and we finally said, okay, we see it in the lab now for the first time, light is traveling as a wave. Okay, great. But then 100 years later, Einstein wrote a paper based on other data on other experiment that had been done repeatedly by other people, but they couldn't figure out, they didn't understand what it meant. And it's called the photoelectric effect, and I'm not going to get all into that now. But it is true that Einstein wrote a paper analyzing this thing called the photoelectric effect, where he said the only way to explain this thing that keeps happening in the lab where basically like light is shot down onto a metal and then electric current like comes up from the metal. And the only way to explain the numbers that kept coming up is Einstein said, I think this doesn't make any sense if we think of light as a wave. We got to think of light as a particle. And so Einstein, I don't know if he literally coined the term, but ever since 1905, we have also discussed light as being made up of these little things called photons, which are supposedly little things. And that's really weird because we had just 100 years ago told ourselves from lab data that light was not made up of little things. But then Einstein came along and said, I know this is going to bother everybody, folks, but and in fact, it's even going to like fly in the face of another paper that I just wrote in the same journal that I didn't get a Nobel Prize for, but that I like more. And Einstein said, I think we got to start thinking of light as being made up of particles called photons. Okay, again, that's like what Yaverbaum is alluding to. And that's true, that did happen. So now physics was really thrown into disarray in 1905. And because now we have evidence saying light is a wave and evidence saying light is a particle. And again, to bring this full circle, that may not sound like that big of a deal because it just sounds like chocolate and vanilla. But what I'm trying to say is that's like saying we have evidence that said lights exist. I'm sorry, we have evidence saying light doesn't exist. And we have and we have evidence saying light does exist. And even if I put it that way, you might say, well, I mean, come on. I mean, if you have evidence saying it doesn't exist, but then you also have evidence saying it does exist, I mean, like go with the evidence that says it does exist. Like, what's the problem? But it is a problem because if light does exist as little things, how the heck can one little thing of light, like how can a little photon of light crash into another photon of light and make no light at all? Like, what's up with that? So then this becomes so what they did was they took Thomas Young's experiment and they, with advanced technology that got more and more advanced in the 20th century and partly due to Einstein, they were able to slow down his experiment and shoot light through two slits, like one particle at a time. Like that's what they tried to do. They tried to take these little photons that in a way Einstein had discovered for us. And they tried to say, all right, well, let's see. I mean, my God, if it looks like light plus light is making no light, let's slow the sucker down. Like, in other words, let's stop shooting like continuous lasers and let's slow this thing. Let's use advanced technology to slow this thing down so much that we just shoot one bit of light out at a time and try to catch light in the act. And let's see what happens when one light goes through a slit, another, like how is one bit of light hitting another light and canceling it out and interfering? Like, let's watch, let's catch light in the act. And what many of you might know or might have heard is once they tried to do that, things got even crazier. Once they tried to catch light in the act, but literally slow down Young's double slit experiment so that they shot one bit of light at a time, even weirder things happen. And when I say weird, what I mean is whenever they actually whenever they could trace one particle, it didn't behave that way. But whenever they missed a particle, it would behave like a wave. Like, it was really elusive. And this is what became the advent of quantum mechanics, which you're not responsible for on the final. But what I want to say is this, like, in the end of the day, when as of 1925 or in all our physics classes or all science classes, when they say, now these days we say light is both, it's a wavicle, it's a wave and a particle, it's a quantum mechanical, or what you'll learn in PChem, like, oh, it's actually a wave function that collapses under these conditions and not. All that crap is really, really weird. We are really saying now that light both exists and doesn't exist depending on what we do with it. It is really weird. It's much weirder than I ever realized when they kept telling me how weird it was. And I don't blame you at all if you're not buying it as I'm telling you. What do you need to know on the final exam is this. It's this. And I know I have 5 minutes left. I'm saying all of this is to say, let's appreciate that when we start looking at things really closely, first of all, it is a real question whether things exist or not. It's really hard to tell, especially the smaller they are. The smaller things are, it's harder to tell whether they are really there as individual things or whether they are just a demonstration of some larger phenomenon that is occurring because of a whole collection of things. When we ask, is something a particle or a wave, we're really asking, is the thing really there or not? Okay, and that becomes really difficult to tell when things are really small. And we care about really small things because everything in the world is made up of really small things. So if we don't know what's going on with the little things that if we don't know what's going on with a brick, how can we possibly understand a brick house is the idea, a brick house, right? And so to bring this all full circle, if you have a bunch of really super tiny particles that you're shooting out of a gun and they're so tiny that you're not even sure you can slow the gun down to shoot one at a time, which is kind of what is going on with elementary or subatomic particles, such as photons or such as quarks or such as like muons and things like that. If they're so small that you can't really tell one thing to do, is see if they demonstrate a Doppler effect or not. Okay, what I'm trying to tell all of you, and this is the part that's on your final exam with the 3 minutes that I have left, I'm saying that actually, if you shoot a bunch of tiny particles and then you run toward the things you're shooting, or you have the thing that you're shooting at run toward you, those two effects, a shift will occur no matter what. A shift in frequency will occur no matter what. But if it's particles you're shooting, the shift will be the same, whether it's source moving in or receiver moving in. But if what you're shooting is waves, then there's a medium involved. And then actually it'll make a difference whether the source is moving or the receiver is moving. Just like it makes a difference whether stars are coming away from us while they send starlight to us, or whether we're moving away from them. It actually makes a difference, because if it's a wave, then when you shoot the wave through the medium, if you're running in toward the wave, you're actually going to shrink the wavelength of the wave when you shoot it. And that's why we get a Doppler effect. Whereas if the receiver is coming in toward the wave, there's no shrinkage of wavelength. Like, it's fundamentally a different phenomenon. Whether the source moves or the receiver moves, either way, say whether the source moves in or the receiver moves in, either way, we'll get an increased frequency, either way. And that is true whether it's particles or waves. But if it's particles, the frequency increase will be identical, whether it's the source moving or the receiver moving. But if it's waves, it will not be identical, because in one case, we're compressing a wavelength, and in the other case, we're not. So the Doppler effect is actually a scientific, quantitative, reliable way to actually, if we have new particles that we just discovered, new things, and we don't know whether they're actually things or not, if they show the details of the Doppler effect as you are being tested on the final, then they show themselves to not be a thing and to be a phenomenon. But if they show an equal Doppler effect for a frequency, for a receiver approach or source approach, then they are things. Okay. So bottom line, with 1 minute left, what do you really need to do on this final exam? And you will get the document, you'll be able to practice and all that, but what do you really need to do? Honestly, what I'm really saying is you need to be able to solve for 4 cases of the Doppler effect if it's waves, and you should be able to solve for 4 cases of the Doppler effect if it's particles. And the latter sounds like the new hard thing, but the latter, if you're following me, is the easier thing. Because if they're particles, there's really just 2 pairs of identical answers. If they're waves, it's 4 distinct answers. And that's how we know, or one way to know whether something actually exists or not. Okay, so that I will get the document to you all. I hope that sort of clarifies sort of something, somehow. But yeah, that's it for now. And thank you very much for being so indulgent and attentive. And if I get any kind of goodbye from anybody, then I will say
have a nice day.
Okay, thank you. You too. You too. All
Thank
right.
you, Professor.
Thank you. Okay.
Thank you, Professor. Have a good weekend.
Thank you too. Hi, everybody.
Thank you, Professor.
Thank you very much. This is Eric Hartman signing off. Thank you. Okay. Thank you very much.